Hello there, everybody, and welcome. This is Professor Thayer with you here today to talk to you about the partition function and ideal gases. But guess what? It's snowing outside. I thought I'd just share that with you. We're in the first major snowstorm of the season, and here I am at work. So let's do this. I'm gonna turn off my video and share my screen with you. Share screen. Good. Okay. And now we'll put this down and we put this up. Oh, there goes the snowplow. Yeah, how come this is not going full? There you go. All right, so I get to my handy dandy pen. All right, so last time we talked about the partition function and we saw about how to calculate it. We saw about Q and calculating that. So the next thing we want to talk about is the general results of our last discussion and applying those to ideal gases following the Boltzmann statistics. We want to consider monatomic, diatomic, and polyatomic gases and build on the ideas of the partition function that it's separable into the degrees of freedom. So there's no time like the present to dive right in and get started. All right, so one. The partition function for monatomic ideal gases. We're going to consider the components of the energy. And now it's kind of nice that things are looking a little more like molecules. Maybe not quite completely. But after doing quantum mechanics, we have moved beyond the electron. And we have some larger things. So the electronic now is only a piece of it. So we have the atomic energy is going to be the sum of the translational and the electronic. Note that there's not any rotational contribution since it's infinitely symmetric because it's a point mass. So we don't have that on, but hold that thought because you never know. It may be coming up soon. All right, the partition function depending on the energy, is also comprised of the same components and is similarly can be decomposed. Components. Now, last time we used the big Q to represent the partition function, but we're actually going to work with the lowercase q now. And the reason is because we're showing that this is the decomposed version. Q of V and T. This is equals Q trans of V and T and times Q. Now, we have a few things we need to note about. This is lowercase because it's decomposed. V is the volume. T is the temperature. Not surprisingly, this stands for translational. Okay, again, V and T is volume and temperature. Elec will be for electronic. Oh, there's our electrons. And did you notice there's no V here? This is only T because the electronic contribution does not depend on the V volume. But translation does depend on V because we need to move it around, right? So we'll separate the partition function into components and then consider each part separately. Sounds a little familiar, doesn't it? Does it remind you of any of the things we talked about in quantum mechanics? Well, that's kind of similar to where we're going. The energy is derived from the energies of particle in a box. Describe the translation of a monatomic gas. Oh, particle in the box is back. Okay, so here's our box. Now we only solved the 2D, right? We didn't solve the 3D. So you got X here, and you got Y here, and wait, X, Y, Z is the height, right? So is this thing in the back. Okay. The energies derived from the PIV describe the translation. Excuse me. Of a monatomic gas. So the energy sub Nx, Ny, Nz equals h squared over 8ma squared times nx squared plus ny squared plus nz squared. So the translational partition function then can be written like this: Q trans equals nx, ny, nz starting for 1 to infinity e to the negative beta e to the nx, ny, and z. These are subscripts. Okay, now, just so we don't forget, this beta, don't forget this one. Okay, this beta is defined to be 1 over KBT because we just got tired of writing it all out every time. So we'll just say beta. All right. This can be broken out into the sum of each of their dimensions. So there's one for each. Okay. So how would this look? All right. Q trans, so basically, oh yes. Start way over here because it's gonna be long. Equals. In other words, you basically can nx separate them out. Separability sounds like, I mean, this is not exactly the same kind of a problem. And then you can sum over n y equals 1 to infinity, sum n z equals, no, does not equal infinity, equals 1 to infinity. Yeah, so it's kind of hard to differentiate exponents, and I don't want to write this whole big thing in teeny letters. So I'm going to write exp. Okay, that just means e to the, just like it's the same thing as this up here. Okay, but I'm just going to do that so I can write it bigger. On here we got this beta, this one right here, h squared over 8m. Yeah, that's an 8ma squared times n sub x squared plus n sub y squared plus n sub z squared. This, and then we close the parentheses. Okay, so let's just remind ourselves that this means the same thing. Just means e to the power of something. It's the same as this. It's e to the x, right? You get what I mean. Okay, it's the same thing as this thing up here. It's the same, e to the x. It's just that when I write it with exp, I didn't then raise it up to the exponent size because there's a lot written here, right? Recall your exponential info, e to the a plus b plus c equals e to the a times e to the b times e to the c. So this is a kind of an interesting thing. E to the, now what this doesn't mean is e to the a plus e to the b plus e to the c equals the product of them. This means e to the sum of some things can be broken out into e to the a times e to the b times e to the c. Okay, just make sure you got that. So now we can apply this to the translational equation, because look at this. This is e2, and then there's a whole bunch of sums up here. All right, so we would need to multiply this out, but you see we would have the sum of a bunch of terms. It's just really the triple product of 3 exponentials. So we could transform it like that. So you would need to multiply it out, which I'm not going to do all the steps, okay, because I'll leave that for you to do. You just multiply this times this, it's FOIL it out, except there's more terms to FOIL. Okay, so next we do Q trans. Yeah, it helps if you do the subscripts to look like subscripts. Q trans equals, oh, no, sorry. Q trans of V and T function equals. Right, you ready? Yeah, all these terms. So now here, this is where we got the sum from. All right, so what do you suppose this one's going to be? Nx equals 1 to infinity of what? Again, I'm going to use the exp instead of doing e to the x, but it means e to the x. Okay, negative beta h squared over 8ma squared. Oh, it's this term. Yep, times nx squared. Because I multiplied this times that, right? And you bring the negative sign along. There it is. All right, that's this one. And now we're going to have a times, because we have this law here. It says if you have the sum of all these things, e to the sum of stuff, you do the product of them. So now here's the next one. I hope I have enough space, but you might even be able to guess what it's going to be. N sub y equals 1 to infinity exp negative beta h squared over 8ma. What's the next one? Wait, is that really right? 8ma squared. Yeah, this is squared, not subscript 2. That makes more sense. Sorry, guys. 8ma squared and ny squared and sub y squared. All right, we're on the edge here. Need more space. All right, times. And now you can probably guess what this one's gonna be. N sub z starts at 1 and runs to infinity. Summation, right? You know about those. Okay, good. Negative beta h squared over 8m8 squared times nz squared. All right. Can this be solved exactly? Well, it's an infinite sum. We can't solve as written, which would be solving it analytically. But it can be represented as the sum of areas of rectangles. Do you remember the Riemann sums? Okay, cannot solve exactly analytically. Yeah. So when we say we can't solve it analytically, we mean we can't solve it using like derivatives and so on. We can't use using I mean, Riemann sums is calculus, but using formulas. Let's put that. We can't solve it using formulas, but we can estimate the area under the curves. Do you remember? Remember the Riemann sums? Recall Riemann sums. You might have done this in a pre-calculus class if you took that kind of thing, or the beginning of your regular calculus class. So here we have f of n, and here we have n, and if you have some bars, so we could even make use of the bars shown here if I were more clever. All right, here we go. We might have something like this, right? And then what you would do is you would get some points in here, like so, and then you would go like that. Okay, the sum as n approaches infinity is approximately equal to, that does not look like an infinity sign, can be approximately equals the area of the rectangles. Right, because you have some of the smaller numbers, but if you don't have a convergent series, then it goes on forever, but you can sometimes approximate it if it's a convergent series. This can be approximated by a function and solved by integration. So just let n be a continuous variable and then integrate. This converts the sum to an integral. So the integral from 0 to infinity of e to the negative beta h squared n squared over 8ma squared dn cubed. This is cubes because it's once for each dimension x, y, and z. right? That's why we have a cube there. And then we actually do the integration. And we'd get Q trans of V and T, this comma, equals pi m dt over h squared to the halves power. Oh, no, wrong line, sorry. Now in Q, can write the average V trans. So remember, we've seen this for the general case already. V trans equals kV T squared dln Q trans over dt with V being held constant. So we saw before, call this one, call and compare. Okay, we had the average energy equals kVt squared d ln Q over dt with N and V constant. Okay, so we saw this already last time. And we also need to recall some other facts. Some math facts. D dx of ln x equals 1 over x, just in case you forgot about that. So we can then solve this, because we're going to actually like take the derivative, and we get that is equal to 3/2. Let me see. I think did we miss? No, we did not. Okay. So you multiply the power. Just 3/2 kVt is the answer. Did you learn this in Gen Chem? So again, we've arrived at a fact you probably learned that E trans equals 3/2 kVt. Now you see why. We just derived it using these equations. Right. Now there's the electronic partition function. This one is kind of important, so I'm going to go ahead and just highlight that for our future reference. I did gloss over a few of the steps on doing the integrations, so I would encourage you to just go ahead and make sure you understand all of those. All right, there we go. Make this nice and neat. All right. So we'll remember that that's important later on. Okay, very good. Next section. The electronic partition function. So remember, at this point, we have done the partition function for translation. Now, next, we're going to do the electronic. How are we doing on time? I did not time this. Great. So here we have our energy levels. I'm going to draw you a little picture. There's the nucleus. Mm. 5. And let's number these. Let's do 1, 2. It's dartboard. No. And then we also have the I equals the level. These are the energy levels in the Bohr model. So we know from the quantum mechanics part that the shapes don't actually all look like this, right? But it can be convenient to use the simplified version when we want to talk about something. So we're gonna go ahead and use the Bohr model. So this is gonna be the energy level. And here's the also the amount of energy on this axis. In other words, this graph has two corresponding things. So when the energy level is 1, which means it's right here in the first orbit, the amount of energy is going to be set to 0 because it's the reference state. And now, do you remember we actually solved harmonic, no, the classical wave equation and the particle in the box, and we saw about the energy levels? It's kind of like this. So there's a big jump here, but then they start getting kind of like closer together. So 3, it's kind of like this. We saw this before. 5, okay. So that's how the energy levels look. So let's just make a few observations. E sub I is the energy level for I equals 1, 2, 3. And of course, you could do more, right? And here we see this, the lowest energy level. Has 0 energy. In other words, it's the ground state. And therefore it's the lowest energy, and we set it to 0. Doesn't mean there's no energy and the electron doesn't move. It means it's the lowest energy state. Which is kind of a little bit of a different thing. All right, great. So with that diagram in mind, now we can write out the Q electronic. So we wrote out the translational one already. Let's now do Q elect as a function of T, temperature equal summation from I G, so EI E to the negative beta E to the sub. That's a little hard to read. Oh, EI, like this. Electronic for the individual number. Okay, let's write out what all these things mean. I equals electronic levels. Okay, in other words, just these Bohr numbers up here that we just saw. Okay, those ones. G equals degeneracy. Oh, remember we saw degeneracy before? We saw it when we had those bead polymers, the 2L configurations. It's like that. E equals energy at the ith electronic level. And E equals the energy level. So in other words, we have, going back to this diagram, the energy level is these, and the energy is on this side. So when you're at the first level, your energy is 0. And this is why we have E and I both. Now, we just said that the lowest energy is 0, but I get a little bit ahead of myself. All right, so let's see. We want to write it out now. The function to break out the sum. Okay, so what we're going to do now is we're going to break out the sum. So here we have Q electronic, and I'm going to start over here because I need a lot of space for this one. Q electronic of T equals G E1 E. This E is different than that E. This E is a subscript E. This E is the natural E, like natural log, the one that goes with that, negative beta. It's a constant. E to the E1 plus G E2 E to the negative beta E, this E energy of E2 plus G E3 E to the negative beta E to the E3 plus blah, blah, blah. You get the idea. And the reason why we can't write them all out is because how do we know what the upper level is? Depends how high they get excited. Now we just said that the lowest energy level has energy of 0 because we set it to 0. So now we have Q electronic of T equals G E1 E to the negative beta sub E to the E1, right? So this term equals 0. So that means this whole thing, anything to the 0 power is 1. So we're going to write this and 1. This is for the whole term. All right, that, whoa. Undo. That whole thing goes to 1. All right. And then we carry all the rest of the terms along. Plus G E2 E to the negative beta E E2 plus G E3 E to the negative beta E to the E3 plus blah, blah, blah. Great. So then we can simplify. Equals G to the E1 right? Because all this went away. We'll just multiply by 1 plus, and then all of these things just carry down. G to the E to the negative beta E2 plus G E3 to the negative beta E3 plus blah, blah, blah. Okay, so note that Q electronic is a function of T, which we tell by this right here, but not V. So using the first and second terms is typically sufficient for T is less than 1,000, which applies to most systems of interest of biologists and chemists. So what will happen if you have a molecule over 1,000 Kelvin? Well, it will probably be burned up. So if you're doing geochemistry, maybe rocks can tolerate that or metals, but room temp is 298, about 300 Kelvin. 1,000 Kelvin is pretty hot. Okay, so what we could say that we generally are going to be working with the first couple of terms only, right? So most often we work with this practical for biological and chemical systems. Yeah, less than. Why? Because remember, if you're at really hot temperatures, do you remember the distribution spreads out to all the different available ones? But when you're in the low temperature, the appreciable population is in the lower energy levels. So you can cut off the empty energy levels and it's not going to cause you any problems. So that's why we could make that approximation most of the time. So now we know how to do the translation in electronic for a monatomic gas. And so the total, right? So actually we should probably highlight this one, right? So now we solve for the Q electronic and we'll keep just this part because that's the part we would most likely want to use. Right, so we've now solved for these two. All right. Good. So now we know this is an important equation, so we can come back to that later. Great. All right. So now we have Q monatomic. Of V and T equals Q trans plus Q elect. Right, and so we could go back and we could write it out, the two. So there we have our solutions, right? We started off with particle in a box and needed that information and talked about Riemann sums and said, okay, let's work out what the answer is for the translational and the electronic. And now we have the two parts. So to get the whole thing for the smaller partition function, you would simply just add those two parts together. And that's it. All right, now next section. Next section. And I apologize, I did not set my timer, so I'm not sure how long we've been going. So I'm just gonna wing it and guess approximately the time we started, which I think was a little before 7 o'clock, I hope. Okay. Related useful properties. Let's zoom in a little more. Related useful properties. Zoomed in a little more than I was before. All right, related useful properties for monatomic gases. Average energy. U, internal energy equals KBT squared. It's d ln Q over dt for constant N and V. This is the total for a monatomic gas. We just did the translational average energy in the previous. This is how we'd know it's the whole system. Yes, we should note this right here. That's why it's a capital letter. Okay. Q is for a component, right? Q is for just a part. Like if you're just doing electronics. So now this is the whole thing. Also, we need N and V to be constant for the total. That's why we have N and V down here like that. All right. So now we're going to switch to the contributions of the parts. Okay, equals N K V T squared D ln Q over dt V. Okay, so notice we have this here, a part. We have N KBT plus N GE2 energy of the E2 e to the negative beta e to the E2 plus N G E3 e to the E3. This is an E. E is in the natural log, negative beta e to the E3 plus blah, blah, blah. This is your average kinetic energy. This is going to be your average electronic energy. Yes, the first term, GE1 does not appear. Because we took the derivative. And it dropped out. Right, it says we have to take the derivative of stuff, and we could work all of that out, but I'm just giving you the answer already. So here it is. All right. Wow. Why stop at the monatomic gas when you could have more than one terms? You could also do this for the diatomic gas. Everything we talked about, this whole thing, starting from the beginning, is all about monatomic gases. Now, we can repeat this for a diatomic gas. And you guessed it, extrapolate for more stuff in the gases. All right. Diatomic ideal gas. So what does it look like? Got two masses. and they are held together by a spring, and I really hope this doesn't delete it. Okay, this is two masses joined by a spring. There it is. That's the spring right there. Here's mass 1 and there's mass 2. So the energy total will be equal to, guess what? A sum. Translation energy plus the rotational energy. Why didn't we have rotational energy before? Well, it was a point mass, right? Plus the vibrational. Why didn't we have that? Well, because it was just a point, right? So we're going to need to use the rigid rotator harmonic oscillator model. All right, so here we have a big Q of N, V, and T. So this whole thing equals Q, small q, because these are the parts, translation, Q rotation, Q vibrational, Q electronic, is raised to the nth power over n factorial. Covering lots of interesting math things. All right, so Q trans. All right, so what we're going to need to do is we're going to need to work on each of the different ones. So what I'm going to do is I'm going to try to help us remember the various ones by giving them some colors. All right, translational is orange, and that's this term right here, and its color is gonna be orange. And here's the Q translational in here. And now we're gonna work on breaking this out, right? So that's the orange one, and we're going to break out its equation. Back to the pen. All right, Q translation of V and T equals, oh, probably the highlighter would be better. All right, Q translational equals 2 pi and one. Where does all this stuff come from? It comes from the fact that we have two masses that are separated by a spring. So it actually comes from working with the reduced mass, which basically puts the mass, basically you deal with the centered mass, the okay. So just if you like to put this whole thing in orange, so you realize this is for Q translational. Do we have orange highlighter? Oh, check it out. We do have orange highlighter. So I'm going to go ahead and do this. Orange Q translation. So we're basically going to take each of the parts because at some point I might want to work with just a piece of it. What happens when you put orange highlighter over orange square? Yeah, it works pretty okay. Okay, that's the translation. All right, next one. All right, do you have anything else to say about this? It looks similar to Q trans of the monatomic gas. Yeah, kind of does. All right. I have a picture to look at. Next. So looks like a energy potential. All right, so we're gonna have something like this. We have this. part. Okay, we need some dotted lines. And that goes to here and crosses over there. All right, we need to go back to our usual thickness. There we go. This is the 0. And yeah, we're also going to have some other important points in here. I should have done all of those with the thin one. Okay. All right, this one, and then we also are going to have something that kind of goes in the middle. Oh, it turned it into a straight line, but the line is now stuck. All right. Okay. Okay, so this is, oh, yep, hold on one sec. One more thing we need. Oh, we're still in the thin one. Okay, great. And we need to go back to the normal thickness. This here, the height between the top and the bottom here, this is gonna be your DE. This is well depth. You see on this graph how the depth of the well is basically approximated by this thing here. This is your first vibrational state. Okay, this line is horizontal, even if it doesn't look. Okay, and now we have this. D0. This is the difference between well depth DE and the first vibrational state. Which is HV over 2. In other words, we could write, okay, let's go back to my pink. DE equals D0 plus HV over 2. Okay, and so what this means is that this one here, okay, that's this distance, but we're also going to talk about this distance, which is HV over 2. All right, so these two things sum up to DE, right? DE is the whole thing, the whole segment. D0 is this top segment, and HV over 2 is this bottom segment. You add up the top and the bottom part, you get the whole thing. There's the equation. All right, so this is about electronic transitions. Okay, so space QLEC is also similar to monatomic. Q electronic equals G E1 E to the DE. Oh yeah, remember that one? That's the well depth. This DE from the picture up here, this thing. DE over KBT plus G E to E to the negative E sub E2 over KBT. All right. We only need the first two terms. Remember, we said before for practical purposes. That's why we only have two here. And this is the equation for the electronic contribution. So let's pick a color to highlight that. It's gonna be, I'll do a light blue like this. This is a different blue than the one we use our aqua one. This is a little different than that. Okay, and this is our electronic, and in here it's this one, and It also should be in this one up here, which it is. Here's the electronic contribution right here. So we'll just make it all nice and color coded. So when we're breaking it out, it's easy to read. All right, so the rotation and vibration, in other words, are the ones that are new. And so we haven't done those ones yet, so we're gonna have to do those ones. And let's color this to make it all look nice. So that everything is organized and nice and clear. This will be something I will not be able to do on the board. Or I'll have to remember I have colored chalks. Maybe I'll do it with chalk that day. All right, there we go. Great. Okay, so now let's come back down here. We got our next one. Now we got the vibrational component, which is new. I don't have that before. The energy of vibrational. Now, vibrational is, this is a V for vibration, and it's gonna be in this fancy V with the little loop on the beginning. Equals. Hopefully help us tell it apart. V plus 1/2 HV for fancy V equals 0, 1, 2, 3. These are the vibrational levels for V equals K over mu to the 1/2 over 2 pi. K equals the force constant. This is not the same K as the KBT K. Diatomic. 2. U is the reduced mass. That means when you have two rotating bodies connected by a spring, you can like average the mass together, and that's the reduced mass. Okay, so two vibe E equals the vibrational level from beginning up to the end is E to the negative V vibrational level equals is summation of V up to infinity of E. I just wrote that one. E to the negative beta V plus 1/2 times HV and this can be solved with geometric series. If you took sequences in series class, you will know what that means. If you do not know what that means, then I'm just giving you the formula. E to the negative 1 over KVT times HV over 2 over 1 minus E to the minus 1 over KVT times HV over 2. So we could simplify. Because who likes writing lots of symbols? We'll have this symbol for vibration is defined as HV over KV. So Q vibe T equals E. And now we have our new vibrational negative vibrational symbol over 2T over 1 minus E minus this funky symbol 5 divided by 2T. Great. So knowing the partition function, we can compute the related properties. Average vibrational energy. The average vibrational energy, again, angle brackets mean average, and kBT squared times dlnq by over dt. We can also compute the molar heat capacity. Bar 3 and 5. So this is the, wait, what is the thing? I don't know. All right, so this thing is at constant volume, and this means the vibrational contribution. The total. All right, so those are the things we can compute for this term. Great. Oh yes, this means we just completed another one of these. So vibrational, we'll give this a color of green. Do we have green available? We do. This is our vibrational term. All right, good. And then we can also go up and find our vibrational term up above. Okay. This vibrational term right here. And here's the vibrational term here. Oops. Okay, so there we have it. Those are those terms. We have one term left that's not yet colored, and that is rotational. Yellow. All right, let's do it. Come over here. Okay. Okay, rotational. Component of the diatomic gas. So the energy levels will come from the rigid rotator. EJ equals H bar J times J plus 1 over 2 I and these are for quantum numbers. J equals 0, 1, 2, blah, blah, blah. Now, we need to make some notes here. All right. J equals quantum number. And I is the moment of inertia. So now we can write the partition function. In the general form, Q equals the sum of G e to the negative beta E J. So now we sub in EJ. For the rigid rotator. All right, let's put it in. So Q rot rotational of temperature equals summation from J equals 0 to infinity, means it could be in any energy level whatsoever, 2J plus 1 e to the negative beta h bar squared times J plus 1 over 2I. This is all the denominator. Now, take a note that this was actually the formula from up here, right? So this thing came from, yeah, and there's one of the H bars came from here. So we'll do and one of the H's, but not both of them. But it gives you the idea, we just substituted that in, and that's what happened there. So the problem is we can't solve this by any expansion method that we know. Do you know how to solve this? Can we solve it? Who solve this? We can't, and neither can anybody else. So we'll resort to setting it up as an integral and solve by integral tables. So that's how we're going to do it. So because this summation does not work, Q rot of t equals integral from 0 to infinity of e to the negative a rotation x over t dx. And then one looks this up on integral tables. And we ask smart math friends, and they tell us the answer is this. E over this thing rotation equals 8 pi squared I kbt over h squared. Or all right, so we've been able to solve this, but we can solve it when basically we're in the regime of low temperatures. Again, because of the distribution of the electrons into the, the conformations into the lower energy levels. So this will work for molecules because at high temperatures, molecules fall apart and they burn. So high temp doesn't really work for them and doesn't really apply anyways because it's not going to be a molecule anymore. So if you are Earth and Environmental Sciences peoples, then this may not be the satisfying solution for you, especially if you're looking in like volcanoes or at other things. But if you are looking at molecules, this is supposed to be about molecules, right? Physical chemistry for life sciences, so hopefully molecules play some part in your thinking. We can solve it in that situation, and this is what we can get. And now, guess what I'm going to say next? Knowing the partition function, we can compute some related property. Oh yes, so what we have now succeeded in getting another answer. So this one's going to be yellow highlight. All right, and yeah, can we now color it? Right, color it. There we go. So in other words, we've once again been plagued by needing to solve these things in perhaps an inexact way. That's one big thing that was really a big lesson to me about physical chemistry is I always thought like we knew everything so certainly. And the truth of the matter is we actually don't. That was kind of a philosophical surprise to me. That is one of these things that there are a lot of these assumptions that we have to make. And yeah, we don't actually know everything, and we solve a lot of things by making approximations. Let's go back to that color-coded equation. Wait, where is it? It's this one right here. The rotational, we now can color this. We now solve this one. And the rotational constant shows up here, and that was our rotation studies. All right, great. So now we've filled this whole thing out. It's pretty good. It's bothering me that this is not clean, nice and clean. Okay, that looks better. All right, good. All right, zoom out again. Now what do you suppose is going to happen next? Well, same thing we did before. Now that we know the partition function, there are some interesting things we could solve for. And that's what we're going to do next. Knowing the partition function, we can compute related properties. What do you suppose I'll calculate next? Can you guess? Average rotational energy. So energy rotational and angle brackets means average will be equal to n kb t squared dlnq over dt, which is n kbt, and we can also get the molar heat capacity. CV equals R, the gas constant. All right, so we've come quite a long way. You could scale this up and do even more, but essentially this is where we're going to look at all the components. So we got a few more notes to go. Rotational, partition function. May not be good enough because we talked about a diatomic. Can take into account symmetry. Okay, so basically what we've done is we just did this, okay, and this is 180 degrees, right? And so sigma equals 2. But you could have a molecule that is like this, like where you have 3 things on it. And so you would then have a smaller degree. Remember, did you do the point groups in your chemistry classes? This is related to the point groups. Right, I think you get the general idea. So now we have looked at all the components of the partition function for the diatomic. Then we could, and we saw that again, our Q total of VNT equals Q trans plus Q rot plus Q vibe plus Q elect. Except instead of pluses, this is really supposed to be multiplication. Sorry, guys. Oops, and we just lost that. Okay, these should be dots. Sorry. Okay, multiply together. And we have now filled them all out. Equals, we can put it all together. 2 pi m. This is the reduced mass. KB T over H squared. This whole thing raised to the 3/2 power times V times T over. So this is the sigma for these sigmas we just drew up here. Sigma. And then we have our rotational symbol times e to the negative. All right, symbol vibration over 2t over 1 minus e to the this thing 5 t times, I hope it all fits in, g 0, no, g sub e 1 e to the Will depth over kBt. This is the first term of the sum. This one has more terms, but we're going to just put the lowest energy. And we see that we have now brought together our parts from all of the different systems, pieces of the system that we looked at. We had the electronic term, which is that one. We had the translational term, which was this one. It took a while to color them all in, so I'll leave that for you to do. I'll leave that for your imagination. The rotational one, which is the yellow one, which is this right here. And we had the green one. The green one is this one right here. And let's label all of these. This is the translation. This is the rotational. This is the vibrational. And this is the start of the electronic. So then we could then extrapolate this to the polyatomic. Which you can then, right, you can extrapolate to polyatomic to make this for real molecules. All right, so there you have it. We have now seen about the partition function and how this applies to all of these 4 terms. And we also saw some interesting things when we did this today, and that is that these partition functions for the ideal gases actually drew on some of the things that we had solved in quantum mechanics, and even a couple of things we didn't solve together in quantum mechanics, but that could have been solved. So then, I hope you enjoyed learning about all these situations. Snow is continuing to fall out there. There's more snow out there than when we started. I did not time this lecture because I forgot to put my watch on. But anyways, hopefully this is a reasonable amount of time. And I hope that you have learned something about how we can use the partition function. So till next time, we'll see you later. Not pause, we need to stop. Yep, bye.